Hi everyone, this is Dr. Hopkins with our next video in our series, reaction mechanisms. And actually it's one of the last ones we're going to talk about in terms of kinetics. And we're going to go a little bit away from our math-based approach or our empirical approach to kinetics and talk a little bit about step-by-step reactions. So a mechanism is the sequence of steps that shows the path from reactants to products. So basically, it's kind of the meat and potatoes of chemistry. This is where the bond breaking and making happens when we go from one to the next. Now, in this class, we won't do a lot of predicting which bonds will break and make. We're just going to make sure that if we see a mechanism, a prediction of what we expect, that it matches up with the actually empirically determined rate law. So they're determined through our empirical measurements. So we're looking at, let's match the math with the actual chemistry or understanding of chemistry. And the steps in the process are typically called elementary reactions. And so an example, if we had a singlet oxygen, another oxygen forming our O2, that would be an example of an elementary reaction. Okay. So elementary reactions are reactions that are basically the stoichiometry of the reaction represents the rate law, okay, or the molecularity, okay. So we can have one that's like a unimolecular reaction, elementary reaction, and that involves just one reactant forming products. We can have bimolecular, where you have two reactants, and we can have trimolecular, where we have three reactants. Now, trimolecular is a little rare because it isn't often the case that three molecules can come together at the same time in order to form a reaction to make products. So oftentimes it might be two and then one, and so it might be two steps bimolecular. So trimolecular is kind of a rare elementary reaction. And so the molecularity, so this unimolecular, is the order of an elementary reaction. So if we talk about a bimolecular process, that's just like we showed before, the rate law for that is second order in oxygen. So notice we show two of them. That means that we have a second order rate law for that reaction. If we go the reverse and let's say O2 falls apart into O and O, that's a unimolecular, and the rate law is just first order in O2 instead of like bimolecular would be second order. Trimolecular would be third order reactions. So a reaction mechanism often has, or reactions often go through intermediates. That means they're neither reactants nor products. And so that means there's something that the reactants form, they generate, and then they get used up to go on to form products in, say, the second step. So we often have these intermediates, and then a reaction mechanism needs to, or a good reaction mechanism needs to sum to the overall reaction stoichiometry, and it has to match, so the rate law. So if we use all of those steps, which we know that if it's bimolecular, it's second order, and so forth, and we put them together, the overall rate law predicted by our mechanism must match the experimentally or empirically observed rate law. So what we're going to do is we're going to focus on evaluating proposed mechanisms. We won't get into predicting mechanisms. You will, if you go on to do other chemistry classes, you will get into the reactivity and predicting reaction mechanisms. So let's start with this. So you have a simple reaction, H2 plus 2ICl, and we're going to form I2 and HCl. And the experimental rate is determined to be first order in each of the reactants, okay? The predicted mechanism is a two-step process where H2 reacts with ICl, so we get H forming an HI bond and an HCl bond, and that's the slow step, okay? And then we also have, so we're going to break this bond to make these two bonds in the first step, okay? So what I mean by a reaction, and that is a slow process, and there's two of, or sorry, actually it's not two of those. No, I can't get rid of that. All right, and then in the second step we have HI reacting with ICl, going to our product I2 and HCl. Okay, so what we have is we are forming a intermediate that is HI that is then going away in the second step. Oops. So the first thing we'll do is check the stoichiometry of the reaction. Okay, so if we add these up, and you can see the intermediate cancels, so that's one way you can figure out it's intermediate. We have one H2, we have two ICLs in this first part right here, right? And then we are forming, this is only, sorry, this should be 1 right here. That's not 2. I've got the step 2 is incorrect. So, because actually it doesn't even make sense in terms of that step. So it sums to that total. So yes, we have our stoichiometry. And if we wanted to predict the rate law, we can use this idea. So if this first step is slow, the slow step is typically what we call a rate determining step. So that the overall rate law is only as fast. So this reaction will only go as fast as the slowest step. And so we would look at this, and if we set the rate law from the elementary reaction, the first one, it's K1, H2, ICl. And those are both first order because that's a bimolecular process in 2. And it turns out that does match the experimental rate law. So this mechanism, once I got rid of that 2, which I had incorrectly in there, does both. It matches the stoichiometry and it matches the rate law. All right, so now we have same reaction, different mechanism. So if we were to propose that the second step was the slow step, we would write the rate law because that's an elementary reaction. We know it's first order in HI and first order in ICl, overall bimolecular, right? So that's what our bimolecular process is. Nice thing about elementary reactions. But we know that we've got HI is an intermediate. An intermediate can't show up in our rate law. Rate laws that we measure empirically only include reactants and products. Intermediates aren't there. So what we need to do is go back to the first step where that was created, and it was created by the reaction of H2 and ICl, a bimolecular, so we would write the rate constant of this, right? And we'd substitute in to our reaction where we would get, we would substitute in for HI, so we'd substitute that in there, and we get K2, K1, which it doesn't really matter. The individual rate constants of the steps can combine to be the same as the experimental rate constant. We'd have H2 first order, which matches our experimental rate law, but we'd have ICl as second order, right? Because we've got 2 of them here, so it doesn't match with the experimental rate law. You can also have reaction mechanisms that have reversibility. So a step you might form a bond, but then it could potentially, if it spends enough time, break back apart and turn into reactants. So let's look at this mechanism where we have a reversible first step, NO plus O2 giving us NO3. That's going to be fast so that it's reversible. Okay, so in other words, the step where NO3 is reacted with NO is slow enough that NO3 has time to go back the other direction. Okay, and so the K1 is the forward. That's our forward. And that's our reverse is K to the minus 1. So we have this step that I said. So that means that basically the forward rate equals the reverse rate. We're allowing this to kind of reverse each other. And so we can write that since the forward rate is a bimolecular process, it'd be K1 NO times O2. The reverse rate is a unimolecular process, and it's K minus 1 NO3. Okay, so let's hold on to that. And then if we look at the overall, okay, because this is the rate determining step, but notice that's an intermediate and can't be included. So we need to substitute in, because notice we had this here, so we can rearrange this equation and substitute in for NO3 so that we would get, so that we're divide that side by K minus 1. So we get K2, K1 over K minus 1. That could be the same as a K observed. And then we have a second order reaction in NO and a first order reaction in O2. And that would be our prediction based on this mechanism. Now notice we didn't have an experimental for that one. But if we had an experimental, we could compare to see if that was correct. So basically, reaction mechanisms are these step-by-step processes. It's actually the chemistry, right? If we're going from bond breaking to bond making, reactants to products. We call each of these steps elementary reactions, which is where we're setting the stoichiometry of that elementary reaction and the order of the reaction the same. And then mechanisms themselves are actually derived from empirical kinetics data and must match that observed rate law. So there's a measurement side to these mechanisms. And then when you move on in further chemistry, you're going to see that there's a chemistry side that isn't always matched with experimental data, but just know that all of those mechanisms you learn later on come from empirical measurements. And if we got a slow step, it makes our kinetics very easy because that's the rate determining step. So until next